Welcome to The Debate. Today, we're diving deep into what's really driving the current revolution in artificial intelligence. Deep learning, it's completely reshaped our technological landscape, right? It's changed everything from medical diagnostics, language translation, you name it. But for those of us tracking this field closely, the kind of central question remains, is this incredible success fundamentally down to better algorithms? Breakthroughs in network design, learning theory, or is it really just the result of, massive computational scale and the sheer amount of data we finally have access to, powering up older ideas? I'm going to argue that the breakthrough really lies in the architecture and these novel learning principles. We've moved past the old limits of AI.
Right, and I approach this from, a slightly different angle. While I absolutely respect the elegance of the models, I really believe what we're witnessing is more a victory of sheer engineering and scaling. Massive data, unprecedented processing power. These are the indispensable ingredients that took concepts that were, let's be honest, mostly academic theories and finally turned them into viable, world-changing applications. For me, scale is the story here.
Okay, I see why you'd prioritize those raw power metrics, but I would argue the primary revolution is almost philosophical. It's the shift away from that legacy of symbolic, logic-based AI, which, let's face it, was pretty much the only game in town when computers were extremely primitive, to a paradigm inspired by biology and mathematics. The real conceptual leap for me was recognizing that data-driven learning built on relatively simple, scalable mathematical principles is inherently, just better than the painstaking, frankly impossible task of writing incredibly complex task-specific programs to handle every single possible input or exception.
But those core mathematical principles, things like the perceptron structure or the basic math behind backpropagation, they aren't exactly new inventions from the last 10 years, are they?
That's true, but they were refined and crucially organized in ways that let the current systems truly function at scale. Consider the deep learning architectures themselves. They're directly inspired by foundational neuroscience, specifically how visual processing is hierarchical. The structure of these deep networks, learning progressively more complex representations layer by layer, that clearly mirrors the organization of the visual cortex, V1, V2, and so on. It really echoes those seminal findings by Hubel and Wiesel way back in 1962.
Right, the edge detectors and so on.
Exactly. That 1962 research established how the brain's early layers process simple features like edges and lines, and then feed that information up to higher layers that recognize complex objects. So this architectural blueprint, this deep hierarchy, that's a profound algorithmic leap. It allows feature extraction to be automated in a way that wasn't possible before.
That's a compelling architectural history, I'll give you that. Though I think that distinction you draw between theory and practical application, that's precisely where we hit the bottleneck. And that bottleneck was only really broken by scaling. These foundational ideas existed decades ago, but their limits were brutally exposed by the lack of computation. It led directly to the AI winter, after Minsky and Papard's famous critique back in '69. The math, the theories of layered networks, they were there, sure, but they just failed to solve real-world problems because the technological capacity was, it was simply insufficient.
But if it were purely a matter of scaling up old concepts, then why did we see the emergence of novel forms of machine intelligence, forms that demonstrated real strategic depth, even back in the 1990s? Think about temporal difference learning, TD learning. Look at TD-Gammon in the early 90s. It achieved world champion level backgammon play entirely through self-play and a pretty sophisticated reward prediction system. Now, this was distinctly different from the kind of pure brute force calculation and search depth that Deep Blue later used for chess. TD-Gammon developed creative, very human-like strategies. It learned when to use a safe move versus a bold play, purely through the elegance of its learning algorithm. It showed internal modeling capabilities that went way beyond just raw speed.
Okay, I grant that TD learning was an important algorithmic innovation, yeah? But the modern context just shows the sheer difference in technological capacity that makes today's deep learning viable. The reason those older ideas, even the refined ones, failed to generalize is precisely because we lack the kind of unprecedented scale available now. I mean, the numbers are just staggering. Computing power today is arguably, what, 1,000,000 times faster, and the memory capacity we can access has increased maybe 1 billion times since the 1980s? This immense scaling doesn't just make things faster, it fundamentally transforms the algorithms. It allows them to move from demonstrating a theoretical principle under lab conditions to becoming practical, effective tools. Tools that can be deployed globally with, manageable training times and acceptable error rates.
Units, the TPUs. They weren't built for general computing, were they? They were specifically developed globally at immense cost to optimize the matrix multiplication that's absolutely essential to these deep learning models. The hardware is literally being driven by the requirements of the learning architectures, optimizing for the unique needs of things like backpropagation and convolutional processes.
I think that slightly overstates the role of architecture, because specialized hardware and scale were frankly a necessity just to handle the staggering data flow, almost regardless of the specific network shape. We know data centers today require massive amounts of energy. The source material suggests something comparable to 34 large power plants, just to manage this flood of zettabytes. This explosion of processing capability and the data availability that goes with it, that's what took the mathematical theories from the 80s and 90s and finally made them viable today. Scale is what provides the foundation necessary for the deep learning to actually function effectively.
Okay, let's focus on the functionality then. Robustness. If the algorithmic architecture isn't the key driver, why did those early expert systems, which were based on incredibly detailed human-crafted rules, ultimately fail to deliver on their promise? I'm thinking of systems like Minsky, designed for expert medical diagnosis. Why did they just collapse under their own weight?
Well, they failed because they relied on human programmers constantly updating rules, manually handling every exception, every ambiguity. The whole knowledge acquisition bottleneck and the combinatorial explosion of complexity just quickly made that rule-based approach completely unfeasible outside extremely narrow, very controlled environments. The genius of modern deep learning, and this is where scale becomes absolutely critical, is its ability to find complex hidden patterns in datasets far too vast for any human team to manually codify. Brute force computation enables that level of autonomous pattern extraction and generalization that something like Minsky couldn't even dream of touching.
Right, that's certainly true regarding the need for scale to find those patterns, yeah. But I think you're missing the algorithmic nuance that allowed scaling to succeed where earlier, pure computation efforts, like the famously failed Psych project, which tried to manually code all of human common sense, just completely collapsed. Expert systems failed because they couldn't really codify the implicit kind of experienced knowledge that human experts relied upon. Deep learning overcomes this because it learns the representations directly from the raw data. And crucially, mere scale wouldn't have delivered the results we see today without key algorithmic refinements. I'm talking about inventions like dropout, for example, a technique that reduces overfitting by randomly ignoring specific network units during training, and the creation of long short-term memory networks, LSTMs.
Ah, LSTM. Okay, while dropout is clever, yeah, LSTMs, they feel more like a really elegant piece of engineering than a fundamental architectural paradigm shift, don't they?
Oh, I disagree fundamentally there. LSTM networks solved a critical architectural problem inherent in recurrent networks, the issue of influence decay over time in sequential data. Before LSTMs, networks really struggled to remember relevant information from, say, 20 steps in the past. That made them practically useless for tasks like comprehensive language translation or complex speech recognition, which absolutely require tracking long-term dependencies. The ability to model these dependencies is what allowed large networks to function effectively at scale. It turned language tasks from a theoretical difficulty into a practical reality. These were indispensable algorithmic innovations that really enabled the scaling you champion.
Okay, I grant that those refinements were necessary steps to make the algorithms functional, sure, but I see them as refinements to the scaling model, essentially maximizing efficiency when you throw massive datasets at them. Let's look at the domains where we've seen established superhuman performance, like the game of Go. AlphaGo famously beat the world champion Qi, and Qi himself apparently said AlphaGo played like a god of the game of Go. You see that as definitive evidence the algorithm is uncovering strategies beyond human understanding, right?
It absolutely is. Deep learning has led to superhuman performance in these highly specialized domains precisely because the algorithms aren't just calculating faster. They are uncovering strategies and patterns, genuinely new knowledge that human experts didn't previously recognize, particularly in complex phases like the mid to late game of Go. And look also at how Google Translate achieved near-human parity in speech recognition. That was a long-standing dream of AI. This really suggests an inherent architectural superiority in learning strategy, not just brute speed.
That's a compelling point, but we need to be careful with the definition of intelligence here. The source material itself reminds us that AI success is currently limited to very narrow domains. The human ability to rapidly generalize, what psychologists call fluid intelligence, solving problems completely outside previous experience, that's still fundamentally superior. I mean, early AI researchers were confounded precisely because skills we consider simple, like basic vision or movement, required millions of years of evolution to develop robustly. Deep learning is powerful, yes, but it's also quite fragile outside its narrow trained context. We haven't yet replicated anything close to general intelligence either through scale or clever algorithms.
But what about the observed effect AI has on human capacity itself? We see human performance in games like chess and Go consistently rising after players compete with or study the moves of advanced AI systems. Doesn't that suggest the machine is somehow imparting enhanced intelligence or understanding?
I think that effect is probably best understood not as the machine achieving true general intelligence, but more like a form of augmented intelligence in humans. Humans are adapting to the machine's relentless computation, its sometimes non-traditional moves. We're learning how to better deploy our own fluid intelligence after encountering the machine's very narrow, very crystallized expertise. In essence, the human brain is adapting to the machine, not the other way around. And that brings us right back to the non-negotiable imperative of scale.
Okay.
I really want to emphasize the sheer necessity of data volume here. Algorithms are just useless without fuel, right? We didn't just need fast computers, we needed massive labeled data sets. Think about ImageNet, the backbone for so many computer vision breakthroughs. It contained over 15 million labeled images. That kind of vast, organized data was simply unavailable previously. And the volume of global data has been what? Doubling approximately every 3 years since the 1980s? This data explosion is what ultimately fed the algorithms, transforming them from theoretical constructs into reality. Data is the foundation. Without it, the theoretical models just remain theoretical.
Well, while the data volume is absolutely necessary, it is the raw material, no question. Data alone is always insufficient. It's just a torrent of bits, mostly noise. The critical intellectual leap is in extracting the underlying, meaningful information from that high-dimensional complexity. We can look at algorithms like independent component analysis, ICA, which has been used extensively in signal processing and early machine learning. These algorithms were designed specifically to find independent hidden components within massive, noisy, high-dimensional datasets. This demonstrates, I think, that the sophisticated algorithm provides the necessary intellectual framework, the structure, to interpret and make sense of those zettabytes of information. It's the mathematical framework that unlocks the data's potential, not the sheer data volume itself that creates the intelligence.
But the success and, crucially, the widespread deployment of algorithms like ICA are only possible because they can be implemented simultaneously across countless servers, mobile devices, data streams globally, something only feasible because of the immense, cheap, and parallel computing power we now possess. Look, the data, the scale, and the algorithm, they are absolutely inseparable components of the current success. But the historical record seems pretty clear that the technological scale was the critical bottleneck. And once that was broken, it finally allowed decades of refined algorithmic theories to actually shine in the real world.
And perhaps that convergence is the most important takeaway here. The deep learning era is fundamentally defined by this necessary convergence of neurobiologically inspired architectures, which provide the learning structure, and specialized learning algorithms, like reinforcement learning, which allow machines to learn complex, often non-obvious strategies purely from experience. This convergence has fundamentally moved us beyond the, frankly, intractable limitations of older symbolic AI, establishing a whole new intellectual paradigm.
And I still maintain that the true turning point, the inflection point, was the realization of scale, the sheer availability of zettabytes of training data and computational power millions of times greater than anything we had in previous eras. These massive technological leaps provided the essential, practical foundation for those pre-existing algorithmic ideas to finally move beyond lab demonstrations and achieve their full practical potential out in the complex, messy real world. Without the scale, the elegance of the algorithm, well, it remains largely an academic footnote.
Ultimately, the AI revolution clearly isn't a singular event, driven by just one factor, but a complex and really fascinating interplay.
Exactly. It's where these sophisticated learning models, refined over decades of work, are brought to powerful, functional life by unprecedented technological scaling. The relationship between sort of pure theory and raw technological power, discussed in the source material, certainly gives us a lot more to think about.